So last lecture, we finished with defining the objects in the solution of the KdV equation. Today's lecture, I want to spend time showing that this is indeed a solution for the KdV equation. And so we're going to start with here. So like I mentioned towards the end of the last lecture, checking by hand that, so actually before I move on, in here, I'm gonna move to the solution for the Kp equation. And the Kp equation is this. And I was doing the KdV equation because I thought it was simpler exposition, but at the end of the day, the objects and the terms that we have are pretty much the same as the KdVs, and the proof for the solution works more nicely in the Kp. So I'm going to do the Kp today, and yeah. So last lecture, I mentioned that if you have this specific solution and then you just try to plug it into the Kp equation, then it's non-trivial to check that it satisfies this equation. You need some special relations for non-trivial cancellations. And this is where the theory of the Riemann surfaces comes in. And the idea is that instead of checking that the equation is satisfied, we're gonna give a characterization of a class of functions so that so instead of checking that the operators act on a certain or like annihilate this function, we just show that they act on a special class of functions in a certain way. And then through this characterization of this space of functions, we're going to be able to get a hold of this identity of solving the Kp equation. And that's what I'll spend some time talking about today's lecture. And I'll be more precise for this. And in particular is we're going to need what's called the Baker-Akhiezer function. And this has very nice properties that will allow us to make precise computations more through its characterization rather than precise computations. And the technology here is really lies in the theory of Riemann surfaces. So, and I think, yeah. So, I mean, one thing to keep in mind, it's kind of like what's going to happen is that, for instance, if we have a polynomial of degree n, and we specify and we know the roots, then that characterizes our polynomial, knowing the roots. And that's all we need to figure out what the polynomial is, up to a multiplicative constant. And for holomorphic functions in the Riemann sphere, if we know its zeros also, all the zeros, then we can characterize the function up to a multiplicative constant. And this story relates to Riemann surfaces, that if we know specific information about its poles in this case, then we can characterize specific functions. So we're going to be trying to get a hold of our functions this way through describing the poles or characterizing them by the poles rather than the differential, trying to solve the differential equation. So this is the claim that I want to prove in this lecture, and it's gonna take me a while, so I'll introduce things to prove this, but this is the ultimate goal. We have that the solution is the second log derivative of this theta function, and the terms in the theta function are defined here. And here I'm actually working just on the case of the torus, where I have a fixed point p infinity, and then I have this billion integrals, which near the near the p infinity point, they have a pole of order k, and then their only singularity or their only principal part is this pole, and then the rest of the term is holomorphic. And there's for this, I didn't mention this in the previous lecture, but there's a precise way to normalize this differential so that they're uniquely defined. And then we have that this coefficients, u, in this case for genus 1, this u, v, w, and v are just scalars. In other genus, they're going to be vectors. So in here, these are just going to be the integrals of the abelian integrals that are defined here. So we defined here 3 abelian integrals. K is 1, 2, and 3. And then the B cycles, the integrals around the B cycles are equal to the constants u, v, and w. And I guess I can mention it right now since it's going to come up. The normalizing feature for this differentials is that the integrals around the A cycles of this abelian are all going to be equal to 0. So this is something I didn't mention in the previous lecture, that to define this uniquely, we need a specific normalization such that these integrals are equal to 0. And this is going to come up in one of the computations later on. And then we have this other constant, which, come on, all right, this other constant d, and this is going to be, we have this b cycle and this pi I, and then this integral of the holomorphic differential. In this case, there's only one holomorphic differential, and it's a constant multiple of the dx over y for genus 1, and so that the A cycle is equal to 2 pi I, and we take an integral from p0 a base point to another point p1. And this is, again, I guess this is also something that I didn't mention. I didn't mention precisely that we also have another fixed point p1. So we have, and again, the b is a scalar, which is the b cycle of the holomorphic form, whose real part is less than or equal to 0. And we have that the theta function is given by this sum of exponentials. In the previous lecture, when I was going through my notes, I noticed that for the definition of the theta function, I actually misplaced the exponential. I put the exponential outside the sum. So that was a typo, but the exponential is inside the sum. So I don't know if you guys probably caught it and were too nice to tell me that I made a mistake. So, but it's fixed. So the previous lecture, we spent time trying to define these things. The only thing that we didn't define was this, but it's, if we already know how to define the other for k equals 1 and 3, then defining this is not that difficult. So we're trying to prove that you define this way is a solution of the KP equation. That's the goal. So the first thing that I'm going to do is I'm going to translate the problem to a consistency equation for linear operators. And this is something that Pat was talking about at the end of the last meeting. And the claim here is that if we have these two linear operators, L2, which is the second derivative with respect to x plus u, and L3, which is third derivative plus u times dx times 3/2 plus v2, then this is actually v. and where u and v are functions of x and t, then u is going to be a solution of the KP equation if these two operators commute. Another interpretation of this is a consistency equation, and another interpretation is that if you have a solution of both you have this relation for a function, this action of the operator of this equation, and this equation for a function, that the t and the y derivatives commute. So this the fact that these two operators commute is equivalent that the operators commute, that the partial derivatives commute for this function psi. And so I think we've seen this type of argument before, and we're somewhat familiar with this, but I'm going to go through the precise computations just so that we have them written down precisely, and we see how how it works. One remark is that in here, this coefficient right now, or this function 3/2 u, at this point, I've chosen it specifically to be 3/2 u, but in later computations, I'm going to make this actually an unknown or independent of u technically, and this one is going to be v2. I'm going to have that these coefficients are independent of this coefficient, and we'll later see that u has to equal to, or v1 has to equal to 3/2 u. But just for simplicity, I went ahead and made v1 equals to 3/2 u. So I'm going to go through the proof and the computations. The proof is a computation. So what we want is that this operators commute. So we have that the commutator of this operators is equal to 0. And in here, the commutator is linear on each of its arguments. So I expand the commutator into the 4 different arguments. This one is 0, partial derivatives commute. And then in this one, this commutator, I like to compute precisely, give a sample computation, and I do it on a test function psi. And here I see how it acts on psi. So first, so this is the commutator for partial t L2, and then I have this partial t acting on psi, so I have partial t, and then this L2 acting on psi, so I have this. And then for this term, I just keep it this way, and I bring it down here. And then this term, for this term, I actually apply the product rule to both terms. To using the product rule, I get the partial of the operator L2 with respect to t, and the operator L2 applied to psi of t. So we have that these two terms cancel out, and that the commutator of partial t and L2 is just a partial derivative of the operator with respect to t. And so that gave me this commutator, and similarly, this commutator is going to be L3 partial derivative with respect to y, and then the commutator of this is this term. So this is what we want to compute, and this is, I'm just gonna briefly go through the details or the computations. So this is L2, and I'm taking the partial derivative, L3 partial derivative, and then I have L3 and L2, and then L2 and L3. And I think probably for this, this is probably a bit better. So when I take the partial with respect to t of this, the only thing that survives is the u, so it's minus ut. When I take the partial with respect to y, the only thing that survives is this term with the y derivative and this term with the y derivative. And then in here, I expand these two operators, the product of these two operators, and I get a bunch of terms. So I just go through the expansion, and in particular, one thing that you have to be careful about is, for instance, when you're expanding this times this, then you have to apply the product rule to this, so that you first apply it to this, and then you apply it to that, and you apply the product rule twice. So it's kind of like this computation. So this is the only thing that's a little bit tricky, just to remember to keep the product rule. So I expand both sides, both operators, and I get all these terms. And the terms in red actually cancel pairwise. So this one cancels with this one cancels with this one cancels with this, V with this, UV with this with this, and this with this. So we have a bunch of pairwise cancellations. And what we have left over is that we have this operator, and this is an element in this algebra of differential operators. And the consistency condition is that the commutator is equal to 0. And if we have a differential operator, then we're expanded in terms of dx, then the only way for this operator to be identically equal to 0 is for each of the coefficients in front of the nth order partial is equal to 0. So that means that this coefficient has to be equal to 0, and this also has to be equal to 0. So we need that the coefficients in front of the partials are each equal to 0, so that this operator is identically equal to 0. So from that, I obtain these two differential equations. So this is from the top one, and this is from the bottom one. And from here on out, what I'm doing is just solving for solving for V in terms of X, or removing V from the system of equations. So in here we have two equations. They have U's and V's, and then I'm just going to use this system of equations to eliminate V from the system of equations. The first thing that I do is that I take the second one and I take the partial with respect to X. And so first I obtain, I keep this inside of the partial, and then I take the partial with respect to X of these two terms. I obtain this. And then from the first one, from the first differential equation, I can actually write an expression for these two terms in terms of U. So I just take the partial with respect to Y of this to obtain this. And then I take the partial with respect to X twice here. And then I obtain this expression. So it gives me the difference between Vyx minus Vxxxx is equal to 3/4 of Uyy minus Uxxxxx. And then I substitute that into here, and then I obtain the KP equation. So this is just a computation, and we're somewhat familiar with it at this point, but I thought it'd be nice to have it written down explicitly. Any questions? So now I think what I wanted to do is I wanted to establish that solving the KP equation is the same as this consistency condition. So to solve the KP equation, I'm going to focus now on the consistency condition. And in particular, to show the consistency condition for these two operators, I'm actually going to find a common solution to these operators. And then with this common solution, I'll be able to eventually show that these two operators commute. But first I need to find the common solution. And this is done through the Baker-Akhiezer function. So again, we're in this scenario where we're on the torus, and we have fixed points P1, P infinity, and P0. P0 is a base point, and then P infinity is going to be an essential singularity of our Baker-Akhiezer function, and P1 is going to be a pole. And this is going to be the important structure from the Baker-Akhiezer function. And in particular, we have, so a lot of times, what we'll see we're gonna take integrals of differentials, and a lot of times we're either going to take the path of integration is gonna be from the base point to P infinity. That's one of the reasons why we're introducing the base point, so that we have a base point of integration, so that the paths are just gonna be defined in this fundamental domain, and they're gonna be independent of so they're gonna be well-defined, or sometimes we're gonna have the integral from P infinity to something else. P infinity will also play a base point. So as a base point. So we have our abelian integrals that we've introduced before. These are going to be functions where these functions are going to have poles of order k at the P infinity point. And additionally, we define these constants u, v, and w to be the b cycles of this abelian differentials. And lastly, we define this constant d, which is going to be an integral from P0 to P1 of the holomorphic differential in the normalized holomorphic differential in the surface, and with this shift. Then we define the Baker-Akhiezer function this way as the ratio of theta functions. So this is actually the term that's going to pop out at the end to give us the solution to the KP equation. But this is going to be the Baker-Akhiezer function, and this is a function on the Riemann surface. So here, P is going to be a point of the Riemann surface, and this is going to be a well-defined function on our Riemann surface. And here, this is where we encode the essential singularities. So I'll give you a second to look at it. Any questions? All right, so let's keep going. And the Baker-Akhiezer function actually has we can show some very specific properties of it. First, we're going to have that aside from the essential singularity at P infinity, this Baker-Akhiezer function is going to be meromorphic on the torus. So the only essential singularity is infinity. And if we evaluate the Baker-Akhiezer function at P1, then P1 is going to be the only pole of our Baker-Akhiezer function. And lastly, we have the asymptotic behavior of the Baker-Akhiezer function near the essential singularity is going to be, the essential singularity is going to be of this type. And we can actually make this more precise in the next one, but we can actually be more precise and say that the Baker-Akhiezer function, the behavior near the essential singularity is going to be 1 plus theta, or not theta, big O. This is big O of C, and times this essential singularity as we approach the P infinity point. So let me go through some of these properties and kind of motivate them a little bit. The the fact that, and kind of like give some intuition or how one could show these things. They're not, I think for the most part, they're somewhat straightforward. The fact that that phi is meromorphic is just, aside from the singularity point, is that this exponential is not going to blow up. We know the behavior of this abelian differentials, and we know that this is only going to be infinity at p infinity. So away from p infinity, these terms are going to be finite. So this is not going to give us an essential singularity. And then these things are just meromorphic functions. The theta functions are actually well-defined functions from, I guess, from C to C, and they have some quasi-periodicity. So the phi functions themselves are meromorphic. So we have that ratio of the phi functions are meromorphic. And the only other place where we could break meromorphic or have essential singularity is this term, but we know the structure of the abelian differentials, and we know that they only have poles at p infinity. And we know the precise description of the poles near that p infinity point. And in particular, we know that the behavior near that p infinity point by the description that we gave for the abelian integrals is given by this. So this really just gives us 1 and 3, which is pretty straightforward. And to actually show, and for 3, we additionally need to show that the theta part, the ratio of the theta functions, doesn't have a pole at that point at p infinity, and we can actually check that precisely here and here, and actually we can check that it's not going to have a pole and its leading term is going to be equal to 1, and you can actually check that pretty easily in here. If you put p infinity, if you set p equals to p infinity, then you can easily check that this integral is from p infinity to p infinity. So this is 0 and this is 0. So you get theta of d times theta ux vy wt d plus d, and in the top you get the same thing. So this ratio cancels out completely if you just set p equals to p infinity, because the integrals are going to be equal to 0. So you can actually you can precisely check that this ratio is equal to 1, and it's essentially by construction that we've introduced this terms theta of d and this theta of the xy_t. And because if you notice, the Baker-Akhiezer function is, like I said, it's a function on the Riemann surface, but these terms are independent of the point P. And the reason that they're introduced is that they're introduced for normalization, so that the leading behavior near P infinity is given by 1. Otherwise, we can remove this, and we can remove this 2 points and have this property by checking that this doesn't have a pole, doesn't go to infinity. And the last thing to check is that the second property, that at the point P1, then we have this integral is equal to, or the Baker-Akhiezer function has a pole, and that moreover it's the only pole of the Baker-Akhiezer function on the Riemann surface. And again, this data function actually doesn't have any poles. The poles are at infinity. So the only way that we can get poles of this Baker-Akhiezer function is if the denominator is 0. And this term doesn't depend on P, so that's gonna be not zero always. And the only term that we need to control and check when that's equal to zero is this term. And so we just need to know the zeros of the theta function. And you can easily check that for P1, or not easily, but it's not too difficult to check that P1 will be, if you put P1 in here and you chase the definition for D, that, and then the definition of theta, then you can actually show it by hand with some computations that this term is going to be equal to zero for P1, right? You're going to have a pole. The thing that's a little bit more tricky is to show that's the only pole. And I didn't look too much into it. I believe Pat gave some arguments for periodic functions on torus of the wire stress P function, finding zeros and stuff like this. Yeah, it takes a while, but the idea would be similar. If you can control the zeros of the wire stress P function, then you can control the zeros of this theta function. And so we can actually, in fact, say that this is the only pole. So we have the specific properties of the Baker-Akhiezer function, and these are key properties in particular because if we have that phi of psi is a function on our Riemann surface such that 1, 2, and 3 are satisfied, then they're going to uniquely define the Baker-Akhiezer function up to a multiplicative constant. So to describe the Baker-Akhiezer function, we actually just need to know these 3 properties. And this is up to a multiplicative constant, and it's going to be the space of functions with prescribed poles in the Riemann surface is fairly rigid. And due to that structure, that's how we can just kind of control the Baker-Akhiezer function and work with it. And this is going to be the key property that we're going to use to prove the U is a solution of the KP equation. The proof for this statement is by the Riemann-Roch theorem. Riemann. When I was looking into this, I found fairly straightforward. I mean, in the way that a lot of textbooks have it is very algebraic, geometry heavy, and it's somewhat sophisticated proofs. But I found a somewhat elementary proof of the Riemann-Roch theorem, and I thought about presenting it, but I think this is going to like deviate us right now too much. But potentially we could look into it a little bit more. What's that? Not with me right now. I just Googled it, and then I found a file, a PDF that was kind of describing it, and they actually went through like this elementary proof, and then they made it more sophisticated in the current language of algebraic geometry. But in particular, it's essentially just like pinning down the poles is gonna somehow like restrict your function. And it's similar to the idea that like if you have a holomorphic function that is constant on the, a holomorphic function on the whole Riemann sphere, then it must be a constant. So it's along these ideas that if you have specific like holomorphicity condition, and for Riemann surfaces, if you have like a prescribed number of poles, then that's going to characterize your function completely. And I think in particular, but in here, one way to the sketch of the proof, how it goes is that essentially what you're going to do is you're going to take a phi tilde function such that it satisfies these three conditions. And you're going to consider the ratio of phi tilde over phi. And when you consider that ratio, the thing that works out very nicely is that this essential singularities cancel. So you don't have essential singularities now because you have the ratio of these two things. And now this is going to be a meromorphic function on the whole Riemann surface. And now you can actually describe now that you have a meromorphic function on all the Riemann surface and you describe its poles, its location of the poles, then that's going to make this function constant. And so this is going to mean that with the pole structure that we've required in condition 2, that means that this ratio has to be a constant. It's going to make the function, this ratio a constant. So then we're going to have that phi tilde, it's going to be a constant times, or psi tilde is going to be a constant of c times psi. So it's really understanding the structure of meromorphic functions on the Riemann surface. And the way that you can go through is through the Riemann rod. And then moreover, since for a Riemann or Baker-Akhiezer function, we actually have a finer control of the behavior near the essential singularity, that if we have 3 prime, this 1 is going to determine this constant c, and it's just going to be 1. So if we actually have just a little bit more control over the asymptotic behavior of the essential singularity, then we can actually pin down the function precisely. We don't need all the knowing the whole thing, just a little bit more. So, and this is what's going to happen at the end, that we're going to be able to analyze the action of the differential operators on the Baker-Akhiezer function. And moreover, we're going to be able to control the asymptotic behavior near the essential singularity. And then from that, we're going to be able to pin down that solution just by knowing the asymptotic behavior. That's going to pin everything down. Questions? All right. So this is going to be the precise claim. We have that the claim is that here psi is my Baker-Akhiezer function defined just now. And the claim is that it satisfies this system of differential equations where the linear operator is L2, as I gave it to you earlier. And here L3, before I wrote this coefficient to be 3/2 u, but in here I'm actually going to make it a free coefficient. They're not a priori. U and B1 are going to be independent, and also B2. But actually the coefficients are actually determined by the Baker-Akhiezer function psi, and they're chosen from the Baker-Akhiezer function, and they're chosen in a way that the asymptotic behavior of the Baker-Akhiezer function after we apply this differential operator is given by this expression. So the essential singularity is going to have this following form near p infinity. So this is the condition that we want to actually be able to control the Baker-Akhiezer function and determine it uniquely. And you might already see what's going to happen. And in here, and when I was talking about this case, if I can control the first coefficient of the essential singularity, of the expansion of this essential singularity, this first coefficient is going to give me this constant multiplier. So in this case, when the coefficient is 1, the constant coefficient is going to be 1. And in this case, I can write this as 0 plus then a linear order. And this constant coefficient is going to force this whole thing to be equal to 0. So this is kind of a prelude to how it's going to end up working out. But at the same time, it's still like loose enough, this condition. We're actually not checking that it's identically equal to 0. We're just checking that the first term in the expansion is equal to 0. And then by this like restrictive structure, it's going to make everything else equal to 0. And since this condition is a lot simpler to check, we can actually engineer our coefficients u and v so that we have this expansion. So this is going to be the strategy, so that we're going to engineer these coefficients. We're going to choose them wisely, and we're going to choose them via the definition of the Baker-Akhiezer function so that we have this expansion. Does that make sense? So it seems kind of like your circular logic a little bit, this statement, but yeah, to me it seems a little bit circular logic. So for me, I wanted to first check that we can actually find these coefficients u, v1, and v2 with just having this condition. And then I'll go through the rest of the argument. So I want to determine the coefficients. So near the essential singularity, I look at the local coordinates and I do essentially a Taylor expansion to obtain this expression for the Baker-Akhiezer function near the essential singularity. And my goal is to have this asymptotic behavior near the essential singularity. So what I'm going to do is I'm going to compute this. So first, I compute partial y of the Baker-Akhiezer function. And in here, it's just, I just do partial y of this. And then that means this coefficients, I should say that xi sub k is a function on x, y, and t, and independent of p, of the point in the Riemann surface. The dependence of the Riemann surface is this point z. So we have this coefficients, c sub k, and then I'm taking a partial with respect to y. So first I do the product rule, and first I do this term, and it's just gonna give me this summation where the partial is applied to each of the coefficients. And then I do the partial with respect to y of this term, and I bring down a c to a minus 2, and then I have this term, and then I have the same exponential term. And again, we want to control this expansion up to the constant term. So for this sum, I just keep the, this is up to the linear term. So I keep all the terms up to the constant term, and the other ones are linear. And then I have this exponential. And so this is dy, and then dx, I do the same thing. I apply the differential, I obtain this expression, and then I apply the differential again. I obtain this expression, and then I keep only the terms up to the linear order, or up to the linear order. And then multiplying times u is just going to be multiplying times u. So I multiply times u, everything else is going to be linear. So I just have this and then the exponential term. So I can precisely in this near the essential singularity, I can carry out the computations explicitly. And what I end up having when I combine all these terms with the L2 and the partial y is that the operator acting on the Baker-Akhiezer function near the essential singularity looks like this. So I have my linear order term, and then I have this term. And what I want to show, or find, or the way that I'm going to determine the coefficients u is so that this is of linear order. So that means that this term has to equal to 0. And now I get this relation, I get this definition of the coefficient u. And u is going to be, this u is the term that's going to be the solution of the KP equation. This is a term of our consistency equation. And we should note that this xi function is determined by the psi function. So it's really given as one of the, so if you have psi, or not psi, zeta, no, not zeta, psi. So if you have psi, it really depends on psi and its expansion of around the essential singularity. So it's determined, it's given by the psi function. So if we have our Baker-Akhiezer function, this is a term that's dependent on the Baker-Akhiezer function. And similarly, if we look at the expansion of this term, it's going to be, we're going to get the following relations or conditions for the V1 and V2 coefficients. And in here, you can note that V1 and U actually are equal to each other up to a multiplicative constant. 3/2 V1 is equal to 3/2 U. So that's what I have in the previous computation. A priori, you don't really need to set this to be 3/2 U, but just simplified computations. And I already knew this computation, so I just simplified it. Otherwise, I need more cancellations or more terms to cancel. So in here, we see that the coefficients of the L2 and L3 operators, we have a precise definition for them, or quote unquote precise. They're still given in terms of expansion of the Baker-Akhiezer function. But actually we can get a better description of this function's u. And in particular, since u is going to be the solution to my KP equation, I want to actually determine this coefficient. So in here, I just wanted to show that we can obtain descriptions of these coefficients based on the Baker-Akhiezer function, and then we can define the L2 and L3 appropriately so that they're solutions, or so that they have this asymptotic behavior. We'll show that the Baker-Akhiezer was a solution. Any questions so far? Okay. So now I want to give the theta function expression for the U1 function. So in here, we have that U, what is it? U is going to be equal to 2 xi 1x. So we want to determine this coefficient. And the way that this coefficient is defined is through this Taylor expansion of this function near the essential singularity. And this is consistent with the way that I did this Taylor expansion of this. So this, the essential singularity gives me this exponential term, and the ratio of the theta functions give me this term. So in here, I remove the essential singularities because the xi k's are determined by this function alone. So what I do is that first I take the logarithm, and the purpose of taking the logarithm is that through the logarithm identities, I can break apart this ratio of theta functions into sums and differences, so that I can work on each part separately. And if I apply the log function to this, then log of this is going to be xi1c plus a second order term. So this is just taking the log of this near c equals 0. Then how we determine this is that if I take the derivative with respect to p, that's really taking the derivative with respect to c, that's gonna give me c1. And then if I take the derivative with respect to x, that's gonna give me the derivative, so sorry. The derivative with respect to c is gonna be give me, it's gonna lead to c1 plus linear order terms. So I actually, to get rid of the rest of the terms, I set c is equal to 0, so that all these other terms go to 0. So I obtain just c1. So this is what I'm doing with the first derivative with respect to p, and then evaluating p equals infinity. So again, c is a local coordinate for p, and we have that for c at p infinity, it's equal to 0. So this is the computation that I'm doing. So this is this computation. So by taking the partial with respect to p and evaluating p at infinity, what remains is going to be c1. And then for my u function, I want the partial with respect to 1 of c1. So I just apply a partial with respect to x. So I actually obtain that my expression for c1 is going to be these two derivatives. And this is going to be equal to minus u over 2. So I have this. I can simplify this further by noting that this term, and so first I can, with the log properties, I can do this plus this plus this, or this plus this minus this minus this. And when I take the derivative with respect to p, I see that this term does not depend on p. So when I take a derivative with respect to p, this term disappears. Then I take a derivative with respect to x. I see that this term doesn't depend on x, and this term doesn't depend on x. So when I take, and since it's a linear combination due to the log, these terms just drop out. So at the end, the only term that depends on both x and p is going to be this term at the top. So taking the partial of p and x is of this term, of the log of this term, is the same as taking the partial of p and x of just this term. So these other terms, these normalization terms, actually just drop out because they're not both simultaneously depending on x and p. So I can actually simplify this expression further to just having this this theta function, which is closer to the description that we have for the u function in the claim at the beginning. But we still have to understand the partial with respect to p, and the p dependence is here. And this is near p equals p infinity. And we can actually do that, and it's not too bad to understand that. We go back to our Riemann bilinear relations. Last lecture I did it for two holomorphic differentials and its complex conjugate. This time I can actually do it for the holomorphic integral and the abelian differential with the first abelian differential, or the second order abelian differential with pole order 1 at p infinity. So what I consider is this integral, and the integral is going to be a contour integral around this region, the fundamental domain of the torus. And by doing the Cauchy or the residue theorem, this contour integral, since everything's meromorphic, then it's just going to be the residue, the sum of the residues of this object inside this region. And the holomorphic integral, this function is going to be holomorphic on all of this region inside. And we actually have one pole arising from this abelian differential. So we have order one pole from here. And so this is what's going to give us a residue. The pole of this object is at p infinity, and it's going to give us a residue, which really means evaluating this holomorphic integral at p infinity. So this, and the holomorphic integral is really the integral of the holomorphic differential from p0 to p. And so we can compute this using the residue theorem. We get this right-hand side. But then we can also do the computation of the line integral using cycles. And this is the same computation that I did in the previous lecture, where I can, A is going to be my cycle, my A cycle for the holomorphic function, and we've normalized it to be 2 pi I. B is going to be my B cycle for the holomorphic differential, and we know that B has a real part less than 0. And then A1 and B1 are going to be the A cycles and B cycles of this abelian differential. And I mentioned this briefly at the beginning of the lecture, is that we normalize this abelian differential so that the A cycle is equal to 0. And we've also defined the B cycle of this abelian differential to be this constant U. This is where the definition of U comes back in. So we actually have that, this integral we can compute in terms of cycles, and we have that A1 is equal to 0, and that A is equal to 2 pi I, and B1 is equal to U. So we obtain that 2 pi I U is equal to 2 pi I, the holomorphic integral at p infinity. So now we're getting a little bit more control over the holomorphic differential, or we have a relation between U and the holomorphic differential. And what we want to control here is this term for this P near P infinity. And so this is this term. We know now that U is equal to this holomorphic integral evaluated at P infinity, and we want to control this. And this is just by the fundamental theorem, this is just the difference of the anti-derivatives, which are the holomorphic integrals. And we have that P is near P infinity. So this is just going to be Z times so this is just going to be the value of the holomorphic integral, the antiderivative times, it's going to be an approximation of this base times height. So this is just going to be the value of the integral at that point times the base, which is going to be just C. And then, so we have expansion of this term in local coordinates. And in particular, we know that this is equal to U. So we have that in local coordinates near P infinity, this term actually equals to minus Z times U, and then a second order term. And so now to compute U, this is the formula we arrived at. And locally, we can exchange this term to be minus U times C. And we have the P derivative is a C derivative, and we're evaluating C equals to 0. And since both of these terms, X and C, have a coefficient equal to U, then the partial with respect to C and the partial with respect to X is actually, and then evaluating CA equals to 0, is equal to the double partial of X, the negative double partial of this function. And so we arrive at the expression for the U function. And now this is the expression that we use for the solution. questions? So I think, so in here, another thing that I want to note is that in here, when I was describing originally the solution of the KP equation of the KDV, I defined this U, V, and W as B cycles of certain differentials that we need to construct, and we need to like normalize, and we need to grab a hold of. But actually, we can actually essentially skip. We can actually come up with formulas that are independent of those differentials, and that only depend on the holomorphic differential. So this is what's happening here, at least in genus 1 case. I suspect that in greater genus, you can also define these coefficients just in terms of the holomorphic differentials. And in particular, we know that the holomorphic differential for hyperelliptic curves is dx over y, well, times a constant to normalize it. And in practice, we can actually take this, we can actually determine this just in terms of the holomorphic differential. And we don't really need to go through the other abelian differentials. So at least in this case, and we can have a precise description of these in terms of this differentials, and then these integrals should then depend on our roots or our branching points E1, E2, and E3. So potentially, once we can describe this with the roots, we can actually give a description of this with the roots. We can come up with a formula based on E1, E2, and E3 for these things. So here in this proof, we actually see a way to compute these coefficients, and it's through the Riemann bilinear identities. So that's a feature that I didn't notice till actually going through the proof, that we can actually have a better description of this coefficients. And actually, yeah, I think for a greater genus, then it's gonna be something like this. Yeah, because actually for greater genus, for genus greater than 0, this is gonna stay true, that the A's are gonna be 0, and then this is gonna be a matrix formula, but A is gonna be a diagonal identity matrix, a diagonal constant matrix. So it's gonna tell you what each of the BIs is gonna equal to. Although it's gonna say that the sum is equal to this. So I think there's a little bit more work. Anyway, so that's that. We have an expression for you in terms of the theta function. And let me now just try to wrap up here and prove that this is true, that the psi is a solution of this differential equation, and the same argument works for L3 and partial t. So we have our Baker-Akhiezer, and when we apply partial y, then we can just go, I'm using shorthand, so for this term, there's a p dependence x, y, t, and x, y, and t, p, x, y, and t. So p, x, y, and t. I can keep it here. This is independent of everything, so I don't put anything here. And then this is dependent on p, so I just keep p here. And this is only dependent on x, y, and t, so I just x, y, and t. And so when I do the partial with respect to y, I just do the again, it's going to be the quotient rule, and then the product rule to obtain this expression. And for this function, you can actually go through the 3 properties of the Baker-Akhiezer function. You can check that it's got to be meromorphic, except at the p infinity point. The behavior near the asymptotic singularity is going to be of the way that we described it, the third property. and the only poles are going to be given at P1. So the only way that we can introduce poles away from the essential singularity is through zeros here, and you can check that the only zeros are the only zeros of the bottom are at P1, and so we see that this function is going to satisfy the 3 characteristics that we want from the Baker-Akhiezer function. So that means since that means that it defines this function up to a constant, that means that the partial derivative with respect to y has to be a multiplicative constant of the original Baker-Akhiezer function. So it acts linearly. So it's just going to be a constant. It's not even going to depend on x, y, and t. It's just going to be a straight up constant of the original Baker-Akhiezer function. And then you can do the same thing for the other terms in the L2 operator. And you'll see that this is going to act linearly on the Baker-Akhiezer function because it's going to, the action is going to keep the properties intact, the 3 properties. So it's going to be a multiplicative constant of the original, and then multiplying by another function of u, it's going to keep the same properties. So everything, all the actions of all these operators is just a linear action. So at the end, when we apply this operator, it's just going to be a constant times the original Baker-Akhiezer function. And then when we look near the essential singularity, we know that this is it has an expansion of this form. And we also know that by the condition that we had on the coefficients u1, v1, and v2, we know that the expansion near the essential singularity of this is of this form. And the only way that, meaning that it has that the constant order is 0, and in this case, the only way that the constant order is equal to 0 is if alpha is equal to 0. So we have that the whole thing is equal to 0. So this is just like the Baker-Akhiezer function is so rigid that and the action of these operators just act on them linearly, and then we can determine this is equal to 0. And now let me just wrap up and show that this operators commute. And again, through the Baker-Akhiezer function, I act on the Baker-Akhiezer function with the commutator of these 2 operators. And in here, since I know that Baker-Akhiezer is a solution of this operator, this is equal to 0. And then this is also equal to 0 because it's a solution. So I have that it's equal to 0. And then I know, then I define the commutator to be this operator, and it's going to be acting on psi, the Baker-Akhiezer function. And what this computation is telling me is that for any p in the Riemann surface, I have that this psi is in the kernel of this operator L. But if L is a differential operator, and if it's not equal to 0, the dimension of this kernel has to be finite. But in here, we found an infinite family of solutions. And the only way that then this contradicts this fact. So the only way that that could be true is if L is identically equal to 0. So that produces this commutator, this operator to equal to 0, the whole commutator equal to 0. And then that tells us that these 2 operators commute, which mean that, I think that's the end, which means that they're consistent, and that means that following the thread, that means that U is a solution of the KP equation. So it all comes through the Baker-Akhiezer function and how rigid it is. So I think that's it for now. Mm-hmm.
So does this proof depend on P infinity being identified early on? and you know exactly what that is.
I'm trying to think how it depends on P infinity. Because we do fix it from the very beginning. And but it could be P infinity could be any point on the Riemann surface. I think the main things that we have to watch out for is that it's distinct from P0, the base point, and P1. And there is some like special cases where, aside from them being distinct, where I do believe that the argument will break down, but
as long as it's in the interior,
yeah,
right?
yeah, and I think essentially what's the P infinity and the PC and the P1, I think essentially what they're going to affect is going to be the initial conditions.
P infinity is what you also define a coordinate at P infinity. So most of what we do is not dependent on coordinate, but the P infinity, right? When you write the Baker-Akhiezer function, you have that assumption, and so yes, that's the issue coming up. So right, you assign a coordinate around infinity, and that is important. So kind of, I think the dependence on it comes to the fact that you also have a coordinate centered at that point.
I feel like all the computations are coordinate independent. I think I can do the transformation for the coordinates and be the same, but maybe in terms of practical implementation, then
Well, because the exact polynomial behavior at infinity, right? It's P of a coordinate, so
yeah, but
what that P polynomial is depends on the coordinate.
actually, but when you go to the solution, I think you see a lot of things come out, or like the certain dependencies come out. So so this is going to be our solution, and I'm trying to see where the P infinity dependence comes here. And in here,
Well, it's the normalization of the differentials.
no, the normalization of the integrals is given by this. Of the differentials is given by just the cycle identity.
Yeah, but the pole behavior depends on the coordinate. The pole behavior is expressed in a coordinate. And I think it's equivalent.
Yeah, I'll have to think about it, how the coordinate. So my impression is that these computations are coordinate independent, and so I don't think that plays a role, and because yeah, so I think that this expansion is going to be somewhat coordinate independent, but I'll think about it more, because
It's expressed in terms of a coordinate, so.
well, because no, but here. No, but here the other thing is that here I defined so U, I end up having this to be I can write it this way, and we see here the dependence on P infinity, but this expression is coordinate independent for you. It is a coordinate independent expression for you.
Yeah,
What's that?
Zeta.
What's that?
Zeta. That does affect, like, it's because it's x times that plus y times the other one, right? So there, but yeah.
Well, no,
there's
but x, these are just like complex variables, and this u, this coefficient is defined with independent of the coordinates. So this solution here is independent of the coordinate that I choose for p infinity.
Yeah, the final solution, the U, V, and W are final solution.
The final solution.
Oh, yeah, you're right, I see what you're saying. Yeah, I was.
The final solution, so I believe, so the arguments, I don't think they're, I have, since the structure of this abelian differentials and abelian intervals is pretty strict, I think that they're independent, the arguments are independent of the coordinates, and by checking the final solution, we see that it's that the coefficients u, v, and w, and d, you can find coordinate independent definitions. So I don't think it depends on the coordinates, but we do see the dependence on p infinity right there. And so I think that this is going to affect the initial conditions. And so, yeah, and I guess if you're trying to like solve an initial condition problem, that the trick is finding the correct p infinities and base points. I don't know if that answered your question.
Yeah, well, I'm trying to tie it to Oswald's book. So he picks a base, what he call base point, and then from that base point you integrate around your loop, you know, gamma A, and you integrate around your gamma alpha, and then you integrate around gamma beta. Those are not independent of the point that you pick, but you have to have some point to start with to do your integration, and that's that.
Yeah, I think.
And from you have a base point. From that base point, that you can identify. You have to identify the phase. Yeah. If you're given a time series. Yeah. If you're given essentially a time series is a solution to the KP equation, right? Yeah. So if you're given the solution, then you need to find the phases. Yeah. And the phases will depend on how you pick the initial points. Yeah. Yeah. Because what they call base point, once you get the base point, then you do all this, you get your phase. Yeah. And here in the definition of D, you also see this base points P0 and P1. So I think, there is this dependence, and for me, it's not very clear how it's going to affect if you change the space points or how it affects the final solution. But I think it seems tricky.
I just wanted to, maybe like this might be going a little bit far ahead, but all the procedures you discussed here, like with the Baker-Akhiezer function, you can modify it just slightly to produce all the conservation laws to the KDB equation. Because if you look at how you define those abelian differentials at infinity, it's like c to the I. Well, if you have a big sum of that times the TIs, those are the higher times. So you're able if you have a G and G solution, the essentially higher genus flows will essentially act to kind of fill the subspace of the Jacobi. So
in here, you mean that
if we go back to how we define
so they're defined right here, U, V, W.
Yeah, but so if you there's the subscript there.
In the gamma B?
No, in the omega.
In the omega, yeah.
Yeah, if you look at so if you had you said like U superscript J, right?
So I guess let me see if I understand. So in here I only define it for 1, 2, and 3. So potentially we can define it for 4, 5, 6, 7, 8, and then you're gonna have so this case can go ... and then this could be instead like X could be T1, this would be T2, this would be T3, and then you can continue doing that.
Exactly, you can get all the conservations clause that way. If you have a genus G surface, there'll be G independent ones, and then you can use the flows of that Baker-Akhiezer function to fill in the full. Find all the solutions.
Yeah, and I think to add to what you're saying, when I was determining the coefficients of the Baker-Akhiezer function, so in here, if I continue this linear expansion, so at the end we know that this is going to be equal to 0. So if I continue the expansion of this, I'm going to have non-trivial terms. But since we know that this is equal to 0, then these terms have to cancel out precisely. And I think this is what
exactly those are the conservation.
These are going to be the conservation laws. This is what Patrick is saying.
But then there's also another way to kind of think about it. You had that picture with the square, and one way to think about it is that the differential you've done a change of coordinates so that the holomorphic differential is just easy. Well, if you rescale it correctly, right? So just the flat differential matches to that. So you mapped it to that, and I think that's kind of behind what sometimes you see.
I see. Yep. So I think for the next time we meet, I thought something that could be useful, or something that I was interested in, was pursuing, where is it? Where did it go? So we came up with this. So I came up with this this description of U in terms of this. So I thought of doing the formula for V and W, and actually, so doing the formula for V and W also, and then actually for the specific for a specific hyperelliptic function where we have E1, E2, and E3, actually computing this in terms of E1, E2, E3. I thought that could be interesting to actually have the use in terms of those roots. And I also thought that it might be interesting to go through the Riemann rock. Yeah, so maybe I'll focus on the Riemann rock and go through that argument. And I think, and then after that, there's also the general genus. But for me, the general genus, I think we don't have to spend too much time